Hi, my name is Tyler Woodby. This is the weather ground for MGA students. So all I've done is I've looked at the ACS and we're going to run through that now. So the composition of the atmosphere is 78% nitrogen, 21% oxygen, and 1% amount of trace gases. Okay? So the next thing we're going to talk about is fog. So what is fog? It's when temperature and dew point are within 3 degrees of each other. That means either the temperature is dropping, the dew point is rising, or the temperature is dropping and the dew point is rising. All of these are just examples of the temperature and dew point coming together to meet. So the acronym that I use is USARIP, okay? And then if you'll zoom in here for the, and just give me a thumbs up when it's good. Okay, so upslope is it moves up the mountain and it cools off. So it has adiabatic cooling. So it's adiabatic cooling. So as it moves up, the temperature goes down, we get fog. Steam fog, okay, that's cold air moves over a warm ground or water. Advection fog is the opposite of that. Warm air moves over cold ground, like in California when you see those clouds coming over the mountain because the ocean is cold. Okay, radiation. So what happens is the sun beats down on the ground all day, and then on a cold, calm night, the ground radiates that energy out, taking the moisture on the ground up with it, so it's rising and cooling, and also the moisture bringing that dew point up to make fog. Industrial fog. The buzzword here is condensation nuclei, and what that means is there's dust in the air from these buildings, and water is attracted to that dust, so more water molecules build up, increasing the dew point. Okay, ice fog, so it's the same thing as when you pull out ice from your freezer, the temperature is going down. And precipitation fog, that's when rain falls into colder air. So it starts at 6,000 and then it drops down to 3,000 and gets so cold that it turns into fog. Okay, so now we're going to talk about the air masses. So air masses are a large body of air with uniform characteristics. Where they get these characteristics is their region of origin, okay? And what we're looking for is the temperature and moisture of those areas. So we have 4 different categories to categorize the air masses. So as you can see, it breaks down to continental, which means land, maritime, which means water, and then polar, which means cold, and tropical, which means warm. So we have continental polar, meaning that it formed over a cold landmass. Polar maritime, right? That means it formed over cold water. Continental tropical, it formed over a hot land, such as the Sahara Desert, okay? And maritime tropical, it formed over hot water, okay? Now we're going to go into low pressure and high pressures, okay? So for this, I use the pinky and thumb trick. For low pressure, I take my right hand and I see that my pinky is turning counterclockwise and that the air is rising. For high pressure, I turn my hand over and see that it turns clockwise and it's descending air. But we're going to go into the list of each. That's just the way that I memorize it. So with low pressure, we have rising air, increased cloudiness, vertical development, precipitation, counterclockwise, typically associated with worse weather. And we're going to take a second to talk about why this is. So when we think about rising air in any scenario, it's going to be worse weather. Why? Because we have stable and unstable air. So we're going to come over here for a second, so you'll follow me at the camera. So stable air, you could think of it as, it's the atmospheric tension and its ability to resist upward force. So you can think of stable air as like a brick. So when an upward force happens, it doesn't move. As opposed to unstable air, you can see is like a piece of paper, so when the upward force hits, it moves up, right? So, and actually we're just going to continue on this until I move back. So we can tell that it's stable air because on our winds aloft chart, we can see that the temperature for every 1,000 feet is decreasing by 2 degrees Celsius, and that happens all the way up to 10,000 feet MSL, okay? So it's not being changed by upward force, so as the air goes up, it cools down. That's how we know that it's stable. When it's unstable and all the temperature and air is mixing together, that's why you'll have differences in temperatures because all of the air is mixing together, okay? And as you can see, Unstable air, if we think about what a cumulus cloud is, a thunderstorm is just a cumulonimbus cloud that looks like a cumulonimbus cloud, right? Because it's going up, because the unstable air is pushing it up. So what are the three things that we need for thunderstorm? Uplifting action, moisture, which is what the cloud is, and unstable air, okay? So that's why, if you'll follow me back over here, when you're thinking of low pressure, instead of memorizing this list, you can just remember that the uplifting action should lead to vertical development, precipitation, and increased cloudiness. That makes sense. And from what I understand, a low pressure is a cold front moving through a warm front. Now we're going to talk about high pressure, okay? Descending air, drier air, clockwise rotation, and typically better weather. And from what I understand, that's just a non-moving cold air mass, okay? So now we're going to talk about the frontal systems, okay? So a cold front, which looks like this, and is characterized by these icicles, okay? It moves faster relative to a warm front. It stays close to the ground, think plow. It creates cumulus clouds and thunderstorms. Again, because the cold front is pushing that air up. So if we think about what's happening, we don't have to memorize the list. Instead, we can fill in the list with our higher order thinking. Okay? It's less stable before and during the passing, and it's better visibility. Why? Because a cumulus cloud takes all the moisture and goes up like this, as opposed to stratus clouds, which cover the whole horizon. So if I look left and right, I'm still covered in moisture, as opposed to the vertical development, which takes all the moisture up here, because even though it's right in front of me, if I look to the right, it's clear for a million. Okay? Now we're going to talk about warm fronts, which look like this, and you can think of these as beads of sweat. They're slower relatively. We see stratiform clouds, steady precipitation, poor visibility, and it's more stable relative to a cold front. Okay? Now we're going to talk about a stationary front, and it's categorized by both of them, right? And it has both characteristics that we talked about, and it will linger for days or even weeks. Okay? Now we're going to talk about occluded fronts. An occluded front is a cold front catching a warm front, catching a cold air mass, okay? This breaks down into two types of occluded fronts, a cold occluded front and a warm occluded front. How we see this on this graph or this drawing is that I have a cold occluded front labeled as 1. So cold, cool is 1, and then cool, cold is 2. So the coldest air is in the back on a cold occluded front, and it meets the cooler cold air in the front. A warm occluded front is the cool cold air catching the warm front, catching the coldest air in the front. Okay? And then that's the weather ground.